Okay, so in our last example, we're going to look at the streamlines in a wind tunnel, and we're going to add some vorticity somewhere in our wind tunnel and see what that does to our streamlines. Okay, so this is going to be a little different. So what I've done here is I've set up Dirichlet boundary conditions around the entire domain. And the reason why I've done that is I want to set the free stream velocity to something here. So let's say 200 centimeters per second, 2 meters per second at the top. And at the bottom, I'm going to have a no slip boundary condition. So the velocity at the bottom is 0. Okay. And I'm going to assume that the east and the west boundary conditions are far enough away that the streamlines will be the free stream velocities at either end of my domain. Okay, so let's apply our Laplace operator, and I've already set up my plot because I feel like we know how to do that now. All right, so let's apply the Laplace operator. Okay, apply it across our domain. All right, so nothing interesting here. All you need to note, well, this is upside down, so we need to change this plot. So let's change you to 90. See what happens. Okay, so here we can see the streamlines, and at the top we have values of around 200 centimeters per second, and at the bottom our values are close to 0. Okay, so nothing interesting, just the linear change in velocity as we approach the ground level. And then now we want to add some vorticity. Okay, so if we add a vorticity value of 200 per se, what's going to happen to our streamlines? Okay, so we have something like this. All right, so the vorticity is positive, and what is happening is the streamlines are being converged, or they're bunching up on the underside of this source or sink term, and that's causing an increased velocity on the underside. If we change this to a negative value, well, that's perhaps affecting our solution too much. So let's just change it to 50. That's too low. Let's change it to 10 so we can actually see what's happening. What about 0? Okay, so if we change the magnitude relative to the surrounding values, we can see how it affects the shape of the streamlines. And that's an interesting result. It means that if the strength of that vortex is greater than the surrounding velocity or the surrounding streamlines, that we're going to have different types of flow regimes. So the use in this example of the partial differential equations is very beneficial to us in visualizing the different flow regimes for different forcing, which will help us to analyze different engineering solutions.